All right. Excuse me. Okay, so what we left off with last week was these classifications, okay? Which there are three of them. We see one of them, and then the preceding two would be the two that preceded this that we talked about were secondary and then also primary. And the reason we said that those are so important is because it depends upon what type of alcohol that you have is going to really determine what its reactivity is. And we still have that same content behind this screen, and we will make sense of that here in just a few minutes. Okay, so when we look at these, as you're writing these down, you might be asking or pondering yourself, so why might something like this be important when we're talking about some of the physical properties? Well, it's more so the identification purposes more than anything else, is what I would be led to believe for our purposes. Because that hydrogen bonding is just so strong that really, really causes that, as you can see, that boiling point to be so much higher. Now, if I remember correctly, tomorrow will be your last day in class, correct? Yes, because Wednesday morning, okay, you have your departure right at 8:35 or something to that extent. Okay, that's right. Okay, so I want to get through this one and then that one. Then we want to talk about things up on the board again. So some of this content would revolve around the organic chemistry part, but what we have on the next slide is Gesundheit, probably more so of a biochemistry application, and then we'll make sense of that when we get there. Okay, and then this is what we were referring to. The idea that because, excuse me, because of this property, all of these OH groups then, when you start attaching multiple ones on there, it makes it more soluble because one of the things those hydroxy molecules can not so much dissolve, but intermix or intertwine with water. So when you put multiple OH groups on any type of substance, your liver then can detoxify whatever it is might be revolving or circulating throughout your body. So then, if it is water soluble, then the liver filters it out, sends it to the bladder, or excuse me, sends it to the kidney, sends it to the bladder, and then exits the body. All right. So what we want to do is make some more sense of this up here, or I should say behind here, because this is where we had left off. One of the things we want you to be aware of is these temperature ranges that we see, okay? And Gesundheit. So with this, okay, with alcohols, we spent time with some of these dehydrations and then oxidizing reactions. So what I would like you to do is, if you have those charts out that are flow charts or mechanisms or whatever it is you want to refer to those. And okay. And then there should be a heading on there, like oxidizing, something to that extent. And I don't know if there's a specific page number for that. Okay. So whatever's on what's on the other side of that? So then, okay. So it's not the one that has the aromatics on there. And I don't know if it makes sense to you to put page numbers on here. We never really have, but maybe that's something that would make sense. But one of the things that we want you to visualize and see, okay, what is the first thing that jumps out in your mind with our parent chains here? The top one, it's a primary alcohol. Then this bottom one is a secondary alcohol. Okay, so according to what we had talked about last week, and on your charts, one of these is going to go through one stage, another one is going to go through two stages. Okay? And with that, I would be led to believe it should say something like oxidation of primary alcohols and then oxidation of secondary alcohols. I don't know if they're on the same sheet. Okay, so with that, which one would appear to be a little more complex? Okay, it would be the primary, and that is because in stage one, what can you interpret that's going to happen with this compound? It doesn't specifically say, hey, go here, this is what happens. It should, I don't know if it actually says what happens, but it shows you what the organic family is, I believe. Okay. Yes. okay, because it has the number 1 up there. And then R is any alkyl group, so then it has this, and then this, and then this, and then it has that on there, okay? So one of the things when we're talking about R groups, notice they don't put all the hydrogens on there. It's always going to be 2 or 3 hydrogens depending upon where it's at in the compound. They don't do this. This one has 2. This one would have 3. But when you're talking about that, you just don't utilize that. So with this, is this a carbonyl carbon? I know that's an R, not a C, but of course that's just a variable. It is. So if that's the case, what type of organic families have carbonyl carbons? There should be 4 of them, okay? So we know there's an ester. There is a ketone. Should have just, rather than trying to. Okay, and I heard this. Then there's one more.
Ether?
Nope, it's not an ether.
Alcohol?
Nope, it's not an alcohol. Nope. You're going to say, oh, I knew that. Nope, it's not amine because those have nitrogens in them. And it does start with an A. Oh, and then we're going backwards. Then it's got a C in it.
Acid.
Yeah, it'd be an organic acid. Those are your 4 compounds that have a carbonyl carbon in it. Okay, so we certainly know it's not an ester, okay, because there's no more R's after this and there's not another oxygen on there, okay? We know it's not a ketone because it's on the end. And then there's not an extra OH group on here. So then that must mean that this is an aldehyde. Okay? So this forms an aldehyde. But that's not where this process stops. That's why it says stage 1. And then it's going to keep on going. There is one exception to that. If you have this one, okay, that's where that process would stop. Okay? But if you have one of these 2, this just keeps right on going. Okay? And I don't know, I just think it says KMNO4 on your charts, right?
It says or K2.
Oh, it says or, okay. All right. So then, since we have this present, this just keeps right on chugging. So rather than just rewriting all this out, we got stage 1. So how do we change this to stage 2 because this reaction continues? You would, okay? We would add that again because it keeps going. But on this, how are we changing this according to your chart? Okay. If we're going to make this into an acid, which it would, you have to put that OH on the end. Okay. For our next reaction, notice we have the same type of reagent. Okay. But you correctly identified earlier that this is not a primary alcohol, but rather a secondary alcohol. So I would be led to believe, and I like to say this again for our purposes, okay, not only is this probably one of the most important organic compounds right here, but it certainly is going through the process of one of the more important products that we can get from here. Because when you see oxidation of secondary alcohols, what can you interpret that this is going to form? The carbons are still going to be there. Okay? There's going to be a double bonded oxygen, and therefore, would we do this? Yeah, this has too many bonds. So then, therefore, we just take that hydrogen back off of there. Okay? And then we form, again, ketones. So when we're looking at these with temperature ranges, these are dehydration reactions. All of those alcohols can go through it, okay? But when we look at oxidations, there's one that just says, I don't want to do this, okay? But we know that primary alcohols can oxidize. We know that secondary alcohols can oxidize. But the moment that we do something like this, okay, because what has to happen with an oxidation reaction is there has to be an adjoining hydrogen that gets stripped off of these. And then notice that's certainly present here. This one has 2 hydrogens, okay? A secondary alcohol just has 1. That's really all it needs. But once we change this to a tertiary alcohol, it just can't. It's just one of the properties that just says, okay, you don't have a hydrogen here, so therefore we can't have you go through this. And then that's a no reaction for tertiary alcohols. It's just how it is. But tertiary alcohols can dehydrate, they just cannot oxidize. Okay, so some of the questions over there, and you might not know what to ask. It's not going to be the last time.
It's gonna be like where the double bonds gonna be. Or like,
Are you asking?
like
Oh,
I just don't get how you know that one was an aldehyde and how you know that one was a ketone. You know what I mean?
because, like you had pointed out, it's where your oxygen's located. So since this is on the end, a double bonded oxygen on the end is going to be an aldehyde. But if it's in the middle, that's why.
So really, you just replace the OH with a double bonded oxygen.
That's exactly what you're doing. Correct. Okay? Because really, when we look at this, okay, from a long, long time ago, okay, one of the things that maybe we'll get to with general chemistry this year is one of the really important aspects to this is when we're talking about oxidations and reductions, okay? Because what happens in oxidation reactions, there's a loss of electrons. So I just like to remember Ole, I guess, because that's a Norwegian thing, okay? And then if it's reduction, then it is gain of electrons. Or I just say, and I'll get it right one of these times. Reduction, electrons are gain. Oxidations, the loss of electrons takes place. Okay, and that is what we see happening here because that electron that we're talking about is coming from that hydrogen there, and it would have come from this hydrogen here, but if we don't have that present because there's a carbon-to-carbon bond, well then there's no electrons to take off of there, and that's why that just can't oxidize.
And then it's tertiary.
Yes, this is a tertiary alcohol. That's correct. That's why
It's always no reaction.
it's always no reaction with oxidations.
So with the,
They can still dehydrate though.
but like with the carbonyl.
Yes, these are your oxidizing agents up here. That's correct. Okay, this only pertains to what you would see as far as changing these to aldehydes, ketones, and acids. Not in that order because the aldehydes and acids go together. Now, one of the things that can happen is we could also start this reaction halfway through. Say you have propanol, okay? Just by saying that, if the suffix ends in al instead of ol, now you know you're dealing with an aldehyde rather than a ketone. All right. So front row middle row. Okay, so last thing that we, and like I said, this isn't the first and last time that we talk about this. That's just not the case. Okay, so the last thing we want to do is, what about if we have to name those alcohols? Same thing applies that you've been doing all year long. What's your longest continuous chain here? Okay, so it's not propane. It's pretty close to that though. If we put an E on there, we would have an alkane, but we have an alcohol, which means the suffix is OL. So if you want to put a 1 on there, yes, you could, but the same thing applies to what we had from prior knowledge. You can call that 1-propene, 1-propene if you wanted to, but it's not necessary. You can just say propene because it's just understood that if that's what you're calling it, that it's after the first carbon. It's once where we do something like this then, where, okay, there's a double bond after the second carbon, then where you'd have to say 2-butene then. If there's nothing written after a number, it's telling you one of two things. Either 1, where the double bond is located, or 2, where an organic family is located. Okay, so we don't need this here. So we've named our propanol. All right. So now, what about if we're looking at, so let's look at this from prior knowledge. What I meant by this was, okay, we certainly know how to name that. Okay, so what would we have here? We still have 3 carbons. It would still be propane. Okay, so 2-methyl. Notice there's something written after that number. Okay, the reason we wanted to make reference to this as opposed to what we see down here is, again, naming this, we certainly know there's still 3 carbons in there. So we don't quite have propanol. Where is that organic family located? It's on the second one. So again, there's nothing written after that number. So it's just telling you where that organic family is located. Here, we put that up there because it's telling us where a derivative is located. So those are 2 different concepts. Okay. Well, you might be it might be, I don't know if you'd be asking yourself this, but what happens if we were to do something like that? Same thing still applies. Okay. How many carbons are in our parent chain? Okay. So therefore, we know the prefix is 6. We know we have, okay, so we're just going to stop there for right now for naming this, okay? Because we have not derivatives, but organic families. For our purposes, we like to say these are organic families, not derivatives like that. So where are those OH groups located? Okay, so they still have to be the lowest numbers. So therefore, we have 2, 3 dash. This is where it gets. This is a little different. You are basing off of prior knowledge. You would be correct, but these are just a little different. 2, 3 hexane. Because you would have said if it was 2 methyl groups, you would say dimethyl, right? But if it's 2 alcohol groups, we want diol, okay? It's the International Union of Applied Physics and Chemistry that, okay, we have to be able to convey this knowledge, and this would be, for our purposes, an accepted name for that. Okay? So what we see happening here then is we can reverse engineer this, just like we've done before. The OL is saying, okay, OL means alcohol. We know that. Okay, di, there must be 2 OH groups located somewhere. Here it's saying we've got 6 carbons in our parent chain, and then this is just telling you where they're at. Okay, so it's just a little bit different than naming these alkanes. That makes these just a little more tricky. All right. Front row, are we? All right. Middle row. All right. So I think that's probably enough for today, so we will catch up to you next time.